I've taught math courses from basic math all the way up to multivariable calculus, and I can help you get the best results in a short period of time. That's today on High Peak Education. Suppose a function f of x has the following graph. If the second degree Taylor polynomial centered at a equals -1 for f of x is this. T2 of x is b x plus 1 squared plus c times x plus 1 plus d. Determine the signs, that is positive or negative, of b, c, and d. Be sure to explain your reasoning for your answers. So a couple thoughts as we get going here. First of all, if you look at T2 here, how would you sort of describe that? If you were to try to put that in words to, let's say, like an late Algebra 1, early Algebra 2 student, T2 would be what kind of function?
Quadratic?
Yes. So
Okay.
x squared is the order of the function. Remember, this is an approximation. What's the reason we do Taylor series or Taylor polynomials? Here's the basic idea. If something is extremely complicated function, or for that matter is a continuous function, many times we want to represent it with a polynomial. We approximate a continuous function with a polynomial, and then we let the calculator just plug into those terms, and we get a good approximation. So here what we're saying is, suppose what's in blue, the function f of x, is a very complicated function. But the Taylor approximation here is an approximation to f of x. But consider this quadratic, it's probably going to fit this function as best we can, like so. See what I just did there? I made it a downward facing what?
Parabola.
If it's downward facing, I think I actually know what the sign, sign, of b is. What would it be?
Negative.
Yes, b less than 0
Yeah, okay, all right, that makes sense.
is just a downward facing parabola, right? Okay, so that's one of the things we know. The next thing we know is the second order term, that is the quadratic term having to do with b, it's calculated from the second derivative of f. So basically what we're trying to do is we're trying to match the concavity. So the thing is, if we're trying to match the concavity, do you see that? Look at the blue and the red curve as I have it sketched now. Would you agree that they're both concave down, negative concavity? If we understand that concave downward is the same thing as b less than 0, is the same thing as a parabola facing downward, then we sort of have the second derivative locked in. But now we have to lock in the first derivative. So locking in the first derivative, that has to do with this term. Okay, so we're thinking about f prime at a. A is the value that we want the Taylor series approximation to be exact at. So in other words, we demand that T2 at x equal to a, we demand that the approximation is exactly equal to the function when x equals a. In other words, we need to anchor it down at least at one point. So that one point would be like right there. You see what I'm saying? The two must be equivalent at that one point. Typically, the structure of the Taylor terms is like x minus a, and then it's either to power 1 or to power 2 and so on. So when a is -1, do you see that we're getting x plus 1 terms repeated in there? Okay, so I bring that to your attention because we actually know that we need to lock in that first derivative at x equal to a, at x equal to -1. So take a close look at the graph, and what would the slope be at that point?
The very top looks just like 0, but then it does slope down.
So that means the sign, sign, of the first derivative should be what? Positive or negative?
Negative.
And so what do you think the sign, sign, of the letter c, the constant, should be?
Negative?
Let me be clear about this. All the x plus 1 does is say, let's approximate at a equals -1.
Okay.
C is what we call the Taylor series coefficient. The coefficient says how much stock or influence, you might say, does that term have? And clearly what we're saying is, well, we want the first derivative to be negative to get as good of an approximation as possible. So that means C should be less than 0. Again, it's a negative slope. Another way of saying that is the Taylor series coefficient should be negative when it's a negative first derivative. Let's now get to coefficient d. Here's the deal. That's the least influential part of the approximation, if you will, because that's just literally a vertical shift by a constant. In some sense, instead of approximating at the origin, 0, 0, how much do we move upward from the origin to get to d?
2.
Yeah, do you see that? So d would be positive. In fact, I'm going to recommend it's probably going to be about positive 2. But in any case, d is definitely greater than 0 because, again, it's a vertical shift to that point. You see it's concave down, so that way a is negative. It's negative first derivative. It got shifted upward, so I think that d should be positive because it's a positive vertical shift. Okay, I think that's it.